Thanks for joining us as we look at an example of using the squeeze theorem for sequences to prove that a sequence converges. So we're going to be looking at, we'll be focusing on one sequence that we call B sub n. But let A sub n, B sub n, and C sub n all be sequences. Suppose that you can show this inequality is true, at least for all integers little n greater than some index big N. So if you can show this inequality is true for all but a finite number of terms of our sequence B sub n, and if you can show the limits of A sub n and C sub n exists and are equal to L, if you can show that these two sequences converge, then you can conclude using the squeeze theorem that the sequence B sub n also converges and converges to L. Okay, let me set that aside. Our example of using squeeze theorem to prove that a sequence converges. We're going to consider a sequence we'll call B sub n, and it'll be cosine of n over n squared plus 1. Okay. L'Hopital doesn't apply. We cannot take the derivative of the top and bottom and help us find this limit. Because, and we can note this, the limit as n goes to infinity of the numerator, that just does not exist at all. Okay. The outputs of cosine oscillate, are some values between -1 and 1 and do not approach any one unique value. So we would say the limit of the numerator does not exist because cosine of n oscillates, let's see if I can spell that, oscillates between -1 and 1 and doesn't approach a unique value. Okay. However, we can observe, even though the sequence doesn't converge itself, the numerator, the terms of this sequence are indeed bounded between -1 and 1. And that gives us hope. Because if this expression is between -1 and 1, and this inequality is true, then we can divide all three terms of the inequality by the same positive expression, and we have our sequence bounded between two less complicated sequences. Okay. Now, so using the squeeze theorem, you want to find two sequences that you know something about. And just to give us a little intuition of what's going on here, let's look at this positive sequence here. Okay. When n is 1, 1 over n squared plus 1 is 1/2. When n is 2, 1 over 2 squared plus 1 is 1/5. And then we get 1/10, and then we get 1/17. And it's pretty clear that the numerator grows without bound, and this sequence, 1 over n squared plus 1, goes to 0. Okay, so we've got evidence here, that this sequence goes to 0. Now, on the left-hand side of this triple inequality, or double inequality, we have negative terms. When n is 1, we get -1/2. When n is 2, we get -1/5. And we get this increasing sequence that also approaches 0. So if we have A sub n and C sub n, both of these familiar sequences converge, and they converge to 0. We'll show that a little more formally, but this is informal, but it shows us where we want to go. Okay, so let me put that aside. Okay. We need to show that the limit as n goes to infinity of these two outer sequences equals some finite number, and that they have the same limit. Okay, and so this first technique, we'll just take we'll look at this sequence here, 1 over n squared plus 1. And so that we can use our reciprocal powers rule, we'll take every term and divide by the highest power of n. So I'll divide everything in the numerator by n squared. And I'll divide all the terms in the denominator by n squared. And anything over itself that is non-zero approaches 1 in the limit. Okay, so we can just use the reciprocal powers law. This will go to 0. So this term goes to 0, and n squared over 1 is 1. So indeed, this limit exists, is 0 over 1, which is 0. And there's nothing in this analysis that wouldn't also work for the sequence here on the left, because even if the numerator is -1, when we divide by n squared and let n go to infinity, the numerator is going to go to 0. Okay. So we've pretty well got our conditions of the squeeze theorem met. Okay. Since this inequality is true, and since the limit as n goes to infinity of the leftmost sequence equals the limit as n goes to infinity of the rightmost sequence equals 0, by the squeeze theorem, we can conclude the limit of cosine of n over n squared plus 1 also equals 0. Proof complete.